Hello everyone, welcome back to the MP Coding Linux Device Driver Development Series with Raspberry Pi. Let's begin a new topic, kernel synchronization techniques. In today's video, we'll focus on one of the most important primitives, the mutex. In our previous examples, we explored how a process waits for data from a device using techniques like blocking I/O, wait queues, poll and select, and asynchronous notification with fasync. All of those mechanisms are about waiting for an event. But mutexes solve a completely different problem. A mutex is used to protect shared data, ensuring that it is not accessed by multiple callers at the same time. Let's understand this with an example. Imagine two processes opening the same device file and both calling right at the same time. Since modern systems have multiple CPU cores, both processes can enter the driver simultaneously and execute in parallel. Now, if both are modifying the same shared buffer without any protection, this can lead to data corruption or inconsistent state. This is where a mutex, short for mutual exclusion, comes into play. A mutex ensures that only one caller can access the critical section at a time. If another caller tries to acquire the mutex while it's already held, it will sleep until the mutex is released. If you're not familiar with synchronization primitives in embedded systems, I've created a separate video series on synchronization primitives in free RTOS. In that series, I explain concepts like semaphores, mutexes, event groups, and message queues, etc., all with practical examples. I highly recommend checking out that series if you want a stronger foundation in these concepts. Now, let's come back to the Linux mutex. Alright, to get started, I've created a simple example kernel module called my_mutex.c, along with a make file. At the moment, this source file is based on the same code we used in the kernel thread example. If you're not familiar with kernel threads, I highly recommend watching that video first before continuing. Now, I've made a few small changes to that previous code. Earlier, we were using simple integer values as task data. But in this example, I've introduced a custom data structure. This structure contains a value, a name field, and a text buffer. Then, I created two instances of this structure, one for each thread. One representing a high-priority task, and the other one for low-priority task. I'll explain what this priority actually means a bit later in the video. For now, just think of them as two tasks with different priorities. Now let's look at what each thread is doing. Each thread runs inside a loop. First, it prints its own data, the task name and its text message. Then, it writes its private message into a shared buffer. After that, it prints the content of that shared buffer. Next, the thread goes to sleep for a duration based on its private data. This creates a timing difference between the two threads. Before starting the next iteration, it prints the shared buffer again. This setup is very intentional. The goal here is to demonstrate why we need a mutex. These two threads are acting as if they are two different processes accessing the same shared memory. Since both threads are updating the same shared buffer without any protection, this can lead to race conditions, where the final output depends on the timing of execution. Now, let's quickly look at the init function. Just like thread example, we create two kernel threads. But this time, we pass a pointer to each thread's private data structure. In addition to that, I've also added a priority configuration for each thread. For now, don't worry too much about how this works internally. Just remember, one thread is set to a higher priority and the other to a slightly lower priority. Toward the end of the video, I'll explain how Linux kernel thread priorities work, along with the theory behind it. In the exit function, we simply stop both threads and print a message. So overall, there's nothing fundamentally new here. This is mostly the same structure we used in the kernel thread example. The key difference is this. Now we have two threads trying to update the same shared memory. What I'm going to show you next is what happens when we do not use a mutex. So let's build this module without any synchronization. Now, let's open the kernel log in another terminal. And insert the module sudo insmod my_mutex.ko. You can see that both tasks, the high priority and the low priority threads, are running. Let's unload the module to stop the threads. Now we can clearly analyze what happened in the kernel log. First, let's understand the timing. If you look at the private data of each task, the high priority task has a value of 10 and the low priority task has a value of 5. Since we multiply this value by 100 milliseconds for sleep, the high priority task sleeps for 1000 milliseconds, which is 1 second, and the low priority task sleeps for 500 milliseconds, which is half a second. Now, let's go through the kernel log step by step. You'll notice that the high priority task runs first and updates the shared buffer. Then it goes to sleep for 1 second. While it is sleeping, the low priority task wakes up, runs, and updates the same shared buffer. In fact, because it has a shorter sleep time, it may run multiple times before the high priority task wakes up again. Then, when the high priority task resumes, it prints the shared buffer. But now the content has already been modified by the low priority task. This is where the real problem begins. Let's think of these threads as two independent processes. Imagine the high priority task is in the middle of updating the shared data. But before it finishes, the low priority task comes in and either reads or overwrites that same data. Now we have a situation where the data may be partially updated or completely overwritten at the wrong time. This leads to data corruption and unpredictable behavior. So what we really need is a mechanism to say, I'm currently updating this shared resource. Please wait until I'm done. And once the update is complete, need to tell second process, okay, now it's safe. You can access it. That mechanism is exactly what a Mutex provides. All right, now let's fix this problem using a Mutex. First, I include the required header file, linux/mutex.h. Then, at the top of the file, I declare a global mutex, static struct mutex, and name it my_mutex. Next, inside the init function, we initialize the mutex using mutex_init and pass the address of our mutex. And in the exit function, we clean it up using mutex_destroy and pass the address of the my_mutex. Now comes the important part, using this my_mutex to protect the shared resource. Inside the thread function, at the beginning of the loop, I acquire the mutex using mutex_lock. This ensures that once a thread enters this section, no other thread can enter until the mutex is released. Finally, before the loop repeats, I release the mutex using mutex_unlock. Between the lock and unlock, it prints its private data, writes to the shared buffer, prints the shared buffer, and goes to sleep. So effectively, the entire critical section, where the shared buffer is accessed, is now protected. This guarantees that only one thread at a time can modify or read the shared buffer. That's all the changes needed in the code. Now let's build the module again, insert it, and observe how the behavior changes with the mutex in place. Insert the module sudo insmod my_mutex.ko. Now you can see that both threads are running. Let's unload the module to stop the threads, and then analyze the kernel log output. First, notice this. When the high priority task starts running, the low priority task does not interrupt it and does not update the shared memory in between. This means the shared section is now properly protected. Now let's look at the pattern in the logs. You'll observe something interesting. The high priority task runs and completes its critical section, then it releases the mutex. After that, it may run again and acquire the mutex once more. After a couple of iterations, the low-priority task gets a chance to acquire the mutex and run. Then it may also run multiple times. So overall, you'll see a pattern like high priority runs a few times, then low priority runs a few times. And this continues. But importantly, they are never running inside the critical section at the same time. Now, why does this behavior happen? This comes down to two things: mutex locking and thread scheduling. When a thread calls mutex_lock, if the mutex is already held, it will sleep until the mutex becomes available. When the mutex is released using mutex_unlock, one of the waiting threads is woken up, but which thread runs next depends on the scheduler. Even though we've assigned different priorities, these threads are still running under the default scheduler policy. So the scheduler is not strictly enforcing real-time priority execution. Instead, it uses a fair scheduling mechanism. Also, remember the sleep timings. The high-priority task sleeps for 1 second. The low-priority task sleeps for 0.5 seconds. Because of this, the low-priority task wakes up more frequently, but it still has to wait if the mutex is held. So what you're seeing is a combination of mutual exclusion, scheduler decisions who runs next, and sleep timing differences. Now time to understand Linux thread priority. If you're coming from an RTOS background, you might already know this behavior. In many RTOS systems, a lower priority task may never get CPU time if a higher priority task is always ready to run. But Linux works a bit differently. So let's briefly understand how thread priority works in Linux. In the Linux kernel, everything is running together, from critical hardware handling to background tasks. So managing priorities correctly is very important to keep the system stable and responsive. In Linux, thread priority is not just a simple number. It is closely tied to the scheduling policy assigned to the thread. Depending on how urgent a task is, the kernel uses different scheduling classes, and each one handles priority in a different way. The first one is the Completely Fair Scheduler, or CFS. This is the default scheduler used for normal tasks. In CFS, we don't use fixed priorities like in an RTOS. Instead, we use nice values, which range from -20 to +19. -20 is highest priority, and +19 is lowest priority. And this is exactly what we used in our example with set_user_nice. CFS tries to ensure that all tasks get a fair share of CPU time, rather than strictly prioritizing one over another. The next category is the real-time, RT, schedulers. These are used for time-critical tasks. In this case, priorities range from 1 to 99, where 99 is the highest priority. Here, priority is strict. A higher priority real-time task can preempt almost anything else in the system. This behavior is much closer to what you see in our TOS environments. I've added some additional details on how to configure these priorities for kernel threads. Please check the README file. I'll upload it to GitHub. For this video, I'm not going too deep into the Linux scheduler internals. But in the future, I'll create a dedicated tutorial where we explore the Linux scheduler in detail. Now, let's test this mutex concept from user space using read and write operations. If you go back to our previous example in the 07 file C DevOps folder, and inside that, the 01 file ops directory, we created a basic character driver to understand Linux file operations. What I'm going to do is reuse that setup. I'll copy the make file and the user space test program, then come to this mutex example, create a new folder called test, and paste those files here. Now, let's open the module source file. Here, we have the usual file operations implemented: open, release, read, and write. And in the init function, we create the character device and use udev to automatically create the device node at /dev/my_cdev0. If you've been following this series, none of this should be new. We've used this setup multiple times. Now, in this example, we are also using a mutex. But in that earlier video, we didn't really focus on explaining it. So let's break it down now. In the init function, we allocate a 64-byte to a character pointer dev_buffer using kmalloc. This buffer acts as our shared memory between different user space calls. We also initialize the mutex here. Now let's look at the read and write functions. To protect access to this shared buffer, we wrap the critical section with a mutex. Here, instead of mutex_lock, we are using mutex_lock_interruptible. This works similarly. It tries to acquire the mutex, but if the thread is put to sleep while waiting, it can be interrupted by a signal. I'll explain the difference in more detail in a moment. The important idea here is both read and write operations are protected by the same mutex, so they cannot access the shared buffer at the same time. Now, to clearly demonstrate this behavior, I'm going to add a 5-second delay inside the write function using msleep. I will add this here after lock the mutex. To use msleep, we need to include linux/delay.h. When a user space process calls write, it will acquire the mutex and then sleep for 5 seconds. During this time, the mutex is still held. If another process tries to call read or another write, it will block and wait. Only after the write finishes and releases the mutex can the other operations proceed. So effectively, we are simulating a long critical section and observing how the mutex enforces synchronization. Now, let's build the module, load it into the kernel, and test this behavior from user space. Alright, the build was successful. Now, let's open the kernel log in another terminal and load the module. You can see the module is loaded and the device node /dev/my_cdev0 has been created. Now I'll open 2 split terminals, one for write and one for read. Here, first, let's perform a write operation. I will write hello test01. Execute the command. You can see that it waits for 5 seconds before completing. That's because the write call is holding the mutex and sleeping. So now, the shared buffer inside the driver is updated with the new message. Now, in the other terminal, let's perform a read, sudo cat /dev/my_cdev0. You can see that it immediately reads back hello test01 from the driver. That's expected because we didn't introduce any delay in the read path. Now let's test the synchronization more clearly. This time, I'll start a write operation with different message, and immediately after that, I'll trigger a read, start the write, and quickly run the read. Now observe this carefully. The read call does not execute immediately. It actually waits until the write operation finishes. Once the write releases the mutex, the read proceeds, and it reads the updated message from the shared buffer. So what's happening here? While write holds the mutex, the critical section is locked. Any read or another write must wait. Once the mutex is released, the next operation continues. Let's try this one more time with a different message, just to confirm the same behavior. Okay, you can see the read waits until the write finishes. After that, it reads with the updated message. Alright, that's it for the examples. Now, let's briefly look at the different mutex locking methods and how they behave when the mutex is already held. The first one is mutex_lock. This will sleep unconditionally until the mutex becomes available. It cannot be interrupted by signals. Next is mutex_lock_interruptible. This also sleeps while waiting for the mutex, but it can be interrupted by a signal. For example, when the user presses Ctrl+C, it's return -EINTR code. Then we have mutex_lock_killable. This is similar, but it only wakes up for fatal signals, not all signals. And finally, mutex_trylock. This one is different, it never sleeps. It tries to acquire the mutex, and if it's not available, it simply returns immediately. Always prefer mutex_lock_interruptible in file operations so that Ctrl+C from user space can unblock a waiting process. I've also added more useful details and notes in the README file, so make sure to check that out as well. That's it for today's video. In the next video, we'll explore another important synchronization mechanism, spin locks. So stay tuned, and I'll see you in the next video.